Good morning everyone. Welcome to this fascinating video on the Higgs boson, the Higgs field, and the Higgs mechanism. These concepts are crucial to understanding the fundamental nature of matter in the universe we live in. In this video, we'll explore the discovery of the Higgs boson, the scientific breakthrough that confirmed the existence of the Higgs field, and the Higgs mechanism, which explains how particles acquire mass. We'll also discuss the implications of these discoveries for our understanding of the cosmos, from the origins of the universe to the fundamental building blocks of matter. Whether you're a student of physics, a science enthusiast, or just someone curious about the mysteries of the universe, you won't want to miss this exciting exploration of the Higgs boson, the Higgs field, and the Higgs mechanism. So, sit back, relax, and get ready to dive into the fascinating world of particle physics. The Higgs boson is a subatomic particle that was first theorized in the 1960s by physicists Peter Higgs, Francis Englert, and Robert Brett. The Higgs boson is a fundamental particle, meaning that it is not made up of smaller particles, and it is a type of boson, a class of particles that obey Bose-Einstein statistics. The Higgs boson is important because it is the particle associated with the Higgs field, which is believed to be responsible for giving particles their mass. The Higgs field is a pervasive field that permeates all of space, and as particles move through it, they interact with the field, which imparts mass to the particles. Without the Higgs field, particles would be massless, and the universe as we know it would not exist. The discovery of the Higgs boson was a major breakthrough in particle physics and was the result of decades of work by scientists at CERN's Large Hadron Collider, LHC. In 2012, two independent teams of researchers announced that they had discovered a new particle with properties consistent with those predicted for the Higgs boson. The discovery confirmed the existence of the Higgs field and provided strong evidence for the standard model of particle physics, the most widely accepted theory describing the fundamental particles and forces that make up the universe. The discovery of the Higgs boson has also opened up new avenues of research in particle physics and cosmology, and scientists are continuing to study its properties and implications. For example, the discovery of the Higgs boson has important implications for our understanding of the early universe and the processes that led to the formation of galaxies and other structures. The Higgs boson also plays a key role in efforts to discover new particles and forces beyond the standard model, which could provide insight into some of the most profound mysteries of the universe. The theory of the Higgs boson was first proposed in the 1960s by physicists Peter Higgs, Francis Englert, and Robert Brett, among others. They were attempting to solve a fundamental problem in particle physics known as the mass problem, which was the question of why some particles have mass and others do not. At the time, physicists had a good understanding of the forces that govern the behavior of particles, but they were struggling to explain why particles have mass. The solution proposed by Higgs, Englert, and Brett was the idea of a new field that permeates all of space, known as the Higgs field. According to the theory, particles interact with the Higgs field as they move through it, much like a surfer moving through water. The Higgs field gives particles mass by slowing them down and creating resistance, similar to the way water slows down a surfer. This resistance, or drag, is what we experience as mass. The Higgs boson is the particle associated with the Higgs field. Like all particles, the Higgs boson is created by the interactions of other particles, and it is short-lived, decaying into other particles very quickly. Over the years, many experiments were conducted to search for evidence of the Higgs boson. The discovery of the Higgs boson was finally confirmed in 2012, after decades of work by scientists at CERN's Large Hadron Collider, LHC. The LHC is a massive particle accelerator that smashes protons together at nearly the speed of light. These collisions produce a spray of subatomic particles, including the Higgs boson. The Higgs boson is extremely rare and difficult to detect, so scientists have to sift through millions of particle collisions to find it. The discovery of the Higgs boson was a major breakthrough in particle physics and confirmed a key prediction of the standard model, the most widely accepted theory describing the fundamental particles and forces that make up the universe. The Higgs boson has since been the subject of much study and research, as scientists work to understand its properties and implications for our understanding of the universe. The Higgs field is a theoretical field that permeates all of space and is believed to be responsible for giving particles their mass. The idea of the Higgs field was first proposed in the 1960s by Peter Higgs, Francis Englert, and Robert Brett, among others, as a solution to the mass problem in particle physics. According to the theory, particles interact with the Higgs field as they move through it, and this interaction gives them mass. The Higgs field is a type of scalar field, which means that it has a single value at every point in space, rather than a direction like other fields such as the electromagnetic field. The Higgs field is not directly detectable, but its existence can be inferred from its effects on other particles. For example, the Higgs field slows down particles as they move through it, creating resistance or drag, which is what we experience as mass. Without the Higgs field, particles would be massless and would move at the speed of light. The importance of the Higgs field lies in its role in the standard model of particle physics, the most widely accepted theory describing the fundamental particles and forces that make up the universe. The Higgs field is an essential part of the standard model, and its discovery provided strong evidence for the validity of the theory. The Higgs field also has important implications for our understanding of the early universe and the formation of galaxies and other structures. In the early universe, the Higgs field played a crucial role in the process of ultra-weak symmetry breaking, which is believed to have separated the electromagnetic and weak nuclear forces, allowing for the formation of matter. The discovery of the Higgs boson, the particle associated with the Higgs field, has opened up new avenues of research in particle physics and cosmology. Scientists are continuing to study the properties of the Higgs field and its implications for our understanding of the universe, including the search for new particles and forces beyond the standard model. The Higgs field is a fundamental part of our understanding of the universe, and its discovery represents a major breakthrough in our understanding of the nature of matter. The mathematics of the Higgs field is quite complex and involves several different concepts from mathematics and physics. In order to understand the mathematics of the Higgs field, it is necessary to have the basic understanding of fields, symmetry breaking, and Gibbs theory. Fields are mathematical constructs that describe the distribution of a physical quantity over space and time. For example, the electric field describes the distribution of electric charge in space. The Higgs field is a scalar field, which means that it has a single value at every point in space. Symmetry breaking is a concept in physics that describes a situation where a system that has symmetries at the fundamental level exhibits a lower symmetry at the macroscopic level. The Higgs field is believed to be responsible for ultra-weak symmetry breaking, which describes the separation of the electromagnetic and weak nuclear forces. Gibbs theory is a mathematical framework used to describe the behavior of fields that are invariant under certain transformations. The standard model, which includes the Higgs field, is based on Gibbs theory. The mathematics of the Higgs field is described by the Higgs Lagrangian, a mathematical equation that describes the dynamics of the field. The Higgs Lagrangian includes terms that describe the interaction of the Higgs field with other particles, as well as terms that describe the Higgs potential. The Higgs potential is a key concept in the mathematics of the Higgs field. The potential describes the energy associated with the Higgs field, and it plays a crucial role in ultra-weak symmetry breaking. The Higgs potential has a Mexican hat shape, which means that it has a minimum at a particular value of the Higgs field. This minimum represents the ground state of the Higgs field, and it is the value of the Higgs field that gives particles mass. The mathematics of the Higgs field also involves the concept of spontaneous symmetry breaking, which is a mechanism by which a system that has symmetries at the fundamental level exhibits a lower symmetry at the macroscopic level. The Higgs field is believed to undergo spontaneous symmetry breaking, which leads to ultra-weak symmetry breaking and the separation of the electromagnetic and weak nuclear forces. Overall, the mathematics of the Higgs field is a complex and highly technical subject, involving concepts from mathematics and physics such as fields, symmetry breaking, and Gibbs theory. The Higgs Lagrangian, the Higgs potential, and spontaneous symmetry breaking are key concepts in the mathematics of the Higgs field, and they play a crucial role in our understanding of the nature of matter in the universe. The Lagrangian of the Higgs field is a mathematical equation that describes the dynamics of the Higgs field in the framework of quantum field theory. It includes terms that describe the kinetic energy of the field, as well as terms that describe its interactions with other fields. The Higgs field Lagrangian can be written as L equals dd v, where L is the Lagrangian, is the Higgs field, d is the covariant derivative, v is the Higgs potential, and denotes the Hermitian conjugate. The first term in the Lagrangian describes the kinetic energy of the Higgs field. The covariant derivative in this term includes the gauge field A, which describes the electromagnetic and weak nuclear forces. The term dd is called the kinetic term and describes the energy associated with the motion of the Higgs field. The second term in the Lagrangian is the Higgs potential, V. The Higgs potential is a function of the Higgs field and has a characteristic Mexican hat shape, with a minimum at a particular value of the Higgs field. This minimum represents the ground state of the Higgs field, and it is the value of the Higgs field that gives particles mass. The Higgs potential also includes terms that describe the interaction of the Higgs field with other fields. For example, the Higgs field interacts with the gauge fields of the weak nuclear force, which are responsible for the weak interactions between particles. The Higgs field Lagrangian is an important part of the standard model of particle physics, which describes the fundamental particles and forces of nature. The discovery of the Higgs boson in 2012 provided strong evidence for the existence of the Higgs field and its potential, and has opened up new avenues of research in particle physics. Overall, the Lagrangian of the Higgs field is a complex and highly technical mathematical equation that describes the dynamics of the Higgs field and its interactions with other fields. It is a fundamental part of our understanding of the nature of matter in the universe, and has important implications for our understanding of the early universe and the formation of galaxies and other structures. The key concepts of the Higgs field are particle mass. The Higgs field is responsible for giving particles mass. In the standard model of particle physics, particles interact with the Higgs field and acquire mass through a process known as the Higgs mechanism. Ultra-weak symmetry breaking. The Higgs field is also responsible for breaking the ultra-weak symmetry that existed in the early universe. This process gave the weak force carriers, W and Z bosons, mass while leaving the electromagnetic force carrier, photon, massless. Higgs boson. The Higgs field is associated with a particle called the Higgs boson, which was discovered experimentally in 2012 at the Large Hadron Collider. The Higgs boson is a scalar particle that is responsible for mediating the Higgs field. Energy. The Higgs field has an associated energy density that contributes to the overall energy of the universe. This energy density plays a role in the dynamics of the early universe and can have implications for the structure of the cosmos. Beyond the standard model, the Higgs field is an important part of the standard model of particle physics, but there are many questions that remain unanswered, such as why the Higgs boson has the mass it does, or how the Higgs field fits in with other fundamental forces like gravity. The study of the Higgs field and its properties is an active area of research in particle physics, with the hope of uncovering new physics beyond the standard model. The Higgs field has an associated energy density, which contributes to the overall energy of the universe. This energy density arises from the Higgs field's self-interactions and its interactions with other particles. The energy of the Higgs field can be described by a potential energy function, known as the Higgs potential. The Higgs potential is a fundamental part of the standard model of particle physics, and describes how the Higgs field interacts with itself and other particles. The Higgs potential has a shape that is often represented by a Mexican hat diagram, which is a two-dimensional plot of the potential energy as a function of the Higgs field. The rim of the hat represents a high-energy state, while the bottom of the hat represents a low-energy state. At high energies, the Higgs field is in a high-energy state, and the Higgs potential is at its maximum. As the universe cools down, the Higgs field undergoes a phase transition, similar to the phase transition that occurs when water freezes into ice. During this phase transition, the Higgs field moves from its high-energy state to a low-energy state, which is associated with the Higgs field's non-zero vacuum expectation value. The energy of the Higgs field also plays a role in the dynamics of the early universe, particularly during the period of inflation, which is believed to have occurred shortly after the Big Bang. During inflation, the universe underwent a rapid expansion, which was driven by the energy of the inflated field. The Higgs field also contributed to the overall energy density of the universe during this period, and can have implications for the structure of the cosmos. The Higgs field interacts with the electromagnetic force through a process known as ultra-weak symmetry breaking. At high energies, the electromagnetic force and the weak nuclear force are believed to be unified, and the particles that mediate these forces, known as gauge bosons, are massless. However, as the universe cooled down, the Higgs field underwent a phase transition, which caused it to acquire a non-zero vacuum expectation value. This resulted in the spontaneous breaking of the ultra-weak symmetry, and the W and Z bosons, which mediate the weak nuclear force, acquired mass through their interactions with the Higgs field. The Higgs field also interacts with a photon, which mediates the electromagnetic force. However, unlike the W and Z bosons, the photon remains massless because it does not interact directly with the Higgs field. The interaction between the Higgs field and the electromagnetic force is important because it gives rise to the phenomenon of Higgs portal dark matter. In this scenario, dark matter particles interact with the Higgs field through the electromagnetic force, which allows them to decay into other particles, including photons. This process can lead to the production of detectable signals in experiments searching for dark matter. Overall, the interaction between the Higgs field and the electromagnetic force is an important aspect of the standard model of particle physics and has important implications for our understanding of the origin of mass and the properties of dark matter. The Higgs mechanism is a fundamental concept in particle physics that explains how particles acquire mass. It is based on the Higgs field, which is a quantum field that permeates all of space. According to the Higgs mechanism, particles gain mass by interacting with the Higgs field. As particles move through the Higgs field, they experience a drag that slows them down, much like a ball moving through a pool of molasses. This drag is proportional to the particle's mass, so particles that interact more strongly with the Higgs field have the greater mass. The Higgs mechanism is important because it provides a way to explain the massive particles without violating the laws of symmetry that govern the behavior of particles. In the absence of the Higgs mechanism, particles would be massless, which would have significant implications for the behavior of matter in the universe. The Higgs mechanism is also important because it is a key part of the standard model of particle physics, which describes the fundamental particles and forces of nature. The discovery of the Higgs boson in 2012 provided strong evidence for the existence of the Higgs field and its role in the Higgs mechanism, and has opened up new avenues of research in particle physics. The Higgs mechanism also has important implications for our understanding of the early universe. According to the Big Bang theory, the universe started out as a hot, dense soup of particles that were in a state of perfect symmetry. As the universe cooled, the Higgs field turned on and particles began to acquire mass through the Higgs mechanism. This process led to the formation of the first atoms, stars, and galaxies, and ultimately to the structure of the universe we observe today. Overall, the Higgs mechanism is a fundamental concept in particle physics that explains how particles acquire mass and has important implications for our understanding of the universe. Its discovery has revolutionized our understanding of the nature of matter in the universe, and continues to be a subject of active research in particle physics. The mathematics of the Higgs mechanism involves the use of gauge theories and symmetry breaking. Gauge theories describe the fundamental forces of nature, including the electromagnetic, weak nuclear, and strong nuclear forces. These forces are mediated by gauge bosons, which are particles that carry the force between particles. Symmetry breaking is a process by which the symmetry of a physical system is broken, leading to the emergence of new properties or behavior. In the case of the Higgs mechanism, the symmetry is broken by the Higgs field, which has an non-zero vacuum expectation value. To understand the mathematics of the Higgs mechanism, we can consider the case of the ultra-weak force, which unifies the electromagnetic and weak nuclear forces. The ultra-weak force is mediated by four gauge bosons: the W, Z, and photon. In the absence of the Higgs field, the ultra-weak force would have a symmetry called ultra-weak symmetry. This symmetry is broken by the Higgs field, which has a non-zero vacuum expectation value. The Higgs field also interacts with the W, and Z bosons, giving them mass through the Higgs mechanism. The mathematics of the Higgs mechanism can be described by the Lagrangian of ultra-weak force, which includes terms that describe the gauge bosons, the Higgs field, and their interactions. The Lagrangian is a mathematical equation that describes the dynamics of the system and the behavior of its particles. The Lagrangian of ultra-weak force can be written as L equals LGAUGE plus LFERMION plus LSCALAR plus LIN, where LGAUGE describes the gauge bosons, LFERMION describes the fermions, particles with half-integer spin, LSCALAR describes the Higgs field, and LIN describes the interactions between these particles. The Higgs field is described by the scalar Lagrangian, which includes a term that gives the Higgs field a non-zero vacuum expectation value. This term breaks the ultra-weak symmetry and leads to the emergence of the W, and Z bosons, which acquire mass through the Higgs mechanism. The mathematics of the Higgs mechanism is highly technical and involves the use of advanced mathematical tools such as group theory, gauge theory, and symmetry breaking. However, it is a fundamental concept in particle physics that provides a way to explain the massive particles and has important implications for our understanding of the universe. Ultra-weak symmetry refers to the unification of the electromagnetic force and the weak nuclear force at high energies, as predicted by the standard model of particle physics. At high energies, the electromagnetic force and the weak nuclear force have similar strengths and properties, suggesting that they may be different manifestations of the same underlying force. This idea was first proposed by Sheldon Glashow, Ed Solom, and Steven Weinberg in the 1960s, for which they were awarded the Nobel Prize in Physics in 1979. The ultra-weak force is mediated by four gauge bosons: the photon, which mediates the electromagnetic force, and the W and Z bosons, which mediate the weak nuclear force. These particles were believed to be massless before the ultra-weak symmetry was broken. The ultra-weak symmetry is broken through the Higgs mechanism, in which the Higgs field acquires a non-zero vacuum expectation value, causing the W and Z bosons to acquire mass while leaving the photon massless. This process also gives particles mass through their interaction with the Higgs field. Ultra-weak symmetry breaking is believed to have occurred in the early universe, shortly after the Big Bang, and had important consequences for the formation of stable atomic nuclei and the overall structure of the cosmos. The Higgs mechanism was proposed independently by three groups of physicists in the 1960s: Robert Brett and Francois Englert, Peter Higgs, and Gerald Guralnick, Carl Richard Hagen, and Lou Kibble. In 1964, Brett and Inlard published a paper proposing the existence of a mechanism by which particles acquire mass in the context of spontaneous symmetry breaking. They showed that a scalar field, which later became known as the Higgs field, could give rise to mass generation in the presence of symmetry breaking. In the same year, Higgs published a paper proposing a symmetry mechanism, but in a more complete and explicit form. He showed that the scalar field would necessarily be accompanied by a new particle, the Higgs boson, which could be detected experimentally. Around the same time, Gurlick, Hagen, and Kibble also proposed a symmetry mechanism independently of the other two groups. Together, these papers laid the foundation for what would later become known as the Higgs mechanism, which is now a fundamental component of the standard model of particle physics. The discovery of the Higgs boson in 2012 by the Large Hadron Collider, LHC, confirmed the existence of the Higgs field and provided experimental validation of the Higgs mechanism. If a Higgs boson became stable, it would have significant implications for the behavior of matter in the universe. First, we should note that the Higgs boson is a particle that is not stable in the sense that it decays into other particles very quickly after it is created. This is due to the fact that the Higgs boson has a large mass and interacts with other particles through the Higgs field. However, if a Higgs boson were somehow made stable, it would have a number of effects on the behavior of matter. One of the most significant effects of a stable Higgs boson would be that it would change the way particles acquire mass. As we mentioned earlier, the Higgs boson is responsible for giving particles mass through the Higgs mechanism. If the Higgs boson were stable, particles would be able to interact directly with it and acquire mass without having to go through the Higgs field. This could lead to a different distribution of masses for particles and could have implications for the structure of matter. Another effect of a stable Higgs boson would be that it could potentially form stable bound states with other particles, much like protons and neutrons form stable bound states in the nucleus of an atom. These bound states could have new properties that are not currently predicted by the standard model of particle physics and could lead to new physics beyond the standard model. Finally, a stable Higgs boson could have implications for the early universe. The Higgs field played a crucial role in the early universe by giving particles mass and breaking ultra-weak symmetry. If the Higgs boson were stable, it could have affected the dynamics of the early universe and could have led to different structures and patterns in the cosmic microwave background radiation that we observe today. Overall, a stable Higgs boson would have significant implications for the behavior of matter and could lead to new physics beyond the standard model. However, it is important to note that there is currently no evidence to suggest that a Higgs boson could become stable, and it is considered highly unlikely by most physicists. Good day.